Okay, let's get down to brass tacks. What does this central limit theorem really say? What it says is it's really easy. It's crazy easy. What it says is this. It says that the means of the sample means, because they're unbiased estimators, they tend towards mu. So in other words, the mean of a sample can be used to approximate the mean of the population. Now, this standard error of the mean thing, this sigma sub x, now this is the key. This is the really big thing that we're able to use. What this thing tends towards is, this is the crazy part. You ready? It's the original population standard deviation divided by the square root of n. And most importantly, because of what we know about sampling distributions, is that these means are normally distributed. Now let me see if I can prove. Let's see if I can prove what I mean with these standard deviations. Watch this. I'm going to change colors. Remember up here we had a mean or a standard deviation back when I used, I'll show you my little distribution thing. Sorry guys, I got a lot going on here, don't I? Remember this guy, when we used these guys? We ended up, I forget, we started with a normal, right? And the standard deviation of the population was 8.2. And when n equaled 10, the standard error of the mean, or the standard deviation of the means of the sampling distribution, was 2.6. Watch this. Let's figure out, is this equal to 8.2 divided by the square root of 10? Well, I got my handy dandy little calculator right here. If I go 8.2 divided by square root of 10, let's see what I get. Well, hush my mouth. This is approximately equal to 2.6. Remember when n equaled 5? Remember, still the same standard deviation of the population. This, by the way, was the bell-shaped distribution, wasn't it? And I think this guy was the skew. Okay? Same population standard deviation. N equals 5. Well, let's see. If I take 8.2 and I divide it by the square root of 5, let's see what we get. 8.2 divided by root 5, and booyakasha, looks like 3.7. Crazy. All right, let's one more time, just because it's so cool to do. All right, 8.2 divided by the square root of 50. Remember, this is what we're saying that the standard error of the mean is. That's, by the way, it's supposed to be a sigma. Standard, wow. Sorry, getting a little late this afternoon. This is, where am I? The standard error of the mean. If I take 8.2 and I divide it by the square root of 50, well, hush my mouth, I get 1.16. Now, okay, that may seem really intuitive. Sorry, I had a little spaz moment. Because this comes from a population. But watch what happens, or excuse me, comes from a population which is normally distributed. Watch what happens when it comes from a population that isn't normally distributed. Let's see, do I get the same thing? Is this equal to 12.51 divided by the square root of 5? Well, 12.51 divided by square root of 5 on my calculator says 5.59, which, if you remember, is what I rounded that from, 5.59. How about this guy? If I take, is this equal to 12.51 divided by root 50? Well, second, whoops, clear, sorry, 12.51 divided by root 50, and I get 1.76, approximately equal to 1.76. Awesome. That's incredible. Now, you may be going, Ripley, okay, that's cool, but it's not as cool as you think it is. Well, okay, maybe. Let's play just a little bit. Let's see if we can put this sucker to work. Now, there are some rules of thumb that we're going to need to discuss in class, but for right now, I just want you to get the beauty of the central limit theorem, all right? Because it's such an amazingly powerful tool. Okay. I'm going to apply it. I'm going to put it into practice. I'm going to show you something. Let's say, just for giggles, that, I don't know, Pepsi's got a 1 liter bottle, okay? of Pepsi. But I hope we all realize that when we're looking at a 1 liter bottle of Pepsi, it's not filled to exactly a liter. All right? I mean, think about that. You got a whole bunch of fillers. Maybe they get gummed up. Maybe they overfill. Maybe they underfill. But Pepsi's claim is that it's got 1,000 milliliters of Pepsi in each 1 liter bottle. That's what 1,000 milliliters is a liter, right? I think so. And let's say that over the course of a lot of observation, they figured out that the standard deviation is 2 milliliters. Okay? All right, so these things are precise, man. That's their claim. Okay, they fill them up to 1,000 milliliters or 1 liter, and they're 2 milliliters off in either direction. Which I mean, I think that we could all live with, right? We understand this. Now, let's say that I take a sample of, I don't know, n equals. Let's say I take, just to keep it simple, I'm going to take just a random sample. I walk into a Pepsi factory and I grab 49 of these things off of a shelf. I pour them into a graduated cylinder, all right? I find that the mean is equal to 999, all right? That's my mean. Here's what I want to figure out. I want to figure out the probability that that sample of 49 quote-unquote 1 liter bottles produces a value that extreme or greater. Now, extreme, I mean that small, okay? Now, watch how this works. Remember when we were just talking about one individual drawn randomly, all right? Drawn randomly from a population. As long as the population was normally distributed, we got to use z equals x minus mu over sigma, right? That was our z-score. Now, I don't know what the distribution is of the Pepsi. I know what its mean is, and I know what its standard deviations are. However, remember, because of sampling distributions, we know that the means are normally distributed, regardless of what the distribution is of the actual Pepsi bottles. We know that the means of the sampling distributions are normally distributed. We know that the mean of the sampling distributions is actually the mean of the population, and that the standard deviation of the sampling distribution by central limit theorem. Now we're kicking into central limit theorem. So think of this right here as when n equals 1. If n is greater than 1, it's x bar, it's the average, minus mu divided by, now remember this, it was the standard error of the means, which we actually know as x bar minus mu over the original population standard deviation divided by the square root of n. Now, why do we get to do that? Why do we get to call this same thing right here? Why do we get to call this, which is very different from this, equal to z? Well, because the means of sampling distributions are a normally distributed variable. And the central limit theorem tells me that the only thing that really changes is this standard error of the mean, and we can account for it by this formula. So watch this. You'll like this. We know that means normally distribute themselves, right? All right? Now, I cannot mess around with what the distribution of the Pepsi bottles is. I don't know what its distribution looks like. I only know what the distribution of the means is. So watch this. I'm going to find a z value. The z value is equal to x bar, right, which I said was 999 minus 1,000 divided by 2 divided by root 49. Haha, you thought I just chose 49 randomly. It's because I'm lazy. All right, so what's that give me? Negative 1 divided by 2/7, which is affectionately known as negative 7/2, which is affectionately known as negative 3.5. Now, remember, as soon as you see z, little bell should go up, ding, ding, ding. We are on this guy, the standard normal curve. It's got a mean of 0. I'm talking about a z-score of negative 3.5. That is way the heck over here. The probability of grabbing a random sample of 49 Pepsi bottles and having them get a value, an average, a mean of 999 or less is this area out here. Well, let's stumble back over to our, let's see, where's my z? All right, so let's see, to the left, if I go negative 3 point, look at this, it doesn't even have negative 3.5 on it. The furthest it goes is negative 3.49. So I know for a fact, where's my paper? If I know for a fact that the probability of getting a z value less than or equal to negative 3.5 is actually going to be less than, what's this thing say? 0.0002. Now, excuse me, what does that really tell us? What does that tell me? Now, in theory, excuse me, we are actually testing the validity of the claim by the Pepsi company, that they're putting a liter of Pepsi in each one of these liter bottles. We're testing that claim. And since I stumbled in and I grabbed a random sample of 49 of these guys and ended up with a mean of 999 milliliters, which is shy. Now you may say, Ridley, 999, it's 1 milliliter shy. Well, if I grabbed a single one, if all I had was a single X value and it was 999, well, the standard deviation for any one Pepsi bottle is 2 milliliters. So this is completely acceptable. However, because I grabbed 49 of them, and their average was 999. The central limit the central limit theorem says, wait, something different is happening here. Now we're talking about distributions of means. We're talking about standard errors of means. Something is fishy. And therefore, it appears, the way we would write this up is, it appears Pepsi's claim, and this is all theoretical, please don't take this to your Pepsi CEO and have me sued. It appears that Pepsi's claim is incorrect. They are underfilling their Pepsi. Now, this is an introduction to hypothesis testing. This is what we do with statistics. This is how we wield the axe of statistics. All right? This is how we prove things. This is how we use it scientifically. This is an introduction to hypothesis testing. And we will go into this far more deeply, hypothesis testing, I think in chapter 9. All right? But I just wanted to just put a little dribble on your tongue there, just because it's so cool. All right. Thanks for your attention. Central limit theorem. All right? Sample means distribute themselves normally. They have a mean of the population mean, which is mu, and a standard deviation, which is called the standard error of the means of sigma divided by root n. And most importantly, we get to talk about this guy right here, sigma over root n. Oh, so cool. So cool. All right. Hope you enjoyed that. We'll finish up the chapter here with binomial distributions, but we're going to go revisit those guys. All right?